Hi everybody, it's Professor Stevens here to explain the greatest integer function, which pairs every real number with the greatest integer less than or equal to less than or equal to x. So I am going to go over this whole thing, but not right away. First, I'm going to do an illustration with example 4, which you can see it here. So that's what we're going for, but I'm going to start completely fresh so you can see me build it up, and we'll read this together. So it says, example 4, applying a greatest integer function. An express mail company charges $20 for a package weighing up to 2 pounds and $2 for each additional pound or fraction of a pound. Let y equals c of x represent the cost to send a package weighing x pounds. Graph y equals c of x for x in the interval 0 to 6. So what we see here is that y is expressed as a function with the function notation, the function c, which is a function of inputs of x. We know that x is going to represent pounds. And since we can have a package just any amount over 0 pounds, because obviously we're not going to send a package that weighs absolutely nothing, but it might be any just a little bit over 0 pounds, but still less than 1 pound, or all the way up to 6 pounds we're allowing here. So notice that we don't include 0, but we are going all the way up to 6 pounds. Okay, so I'm going to start mapping out the axes. So the x-axis is pounds. Okay, and we can start at 0 but not include it and go all the way up to 6. So there's my pounds, and then I'm going to start at $20 for packages weighing up to 2 pounds. So starting at 2 pounds, or not starting at 2 pounds, starting at just slightly more than 0 pounds all the way up to 2 pounds, I'm going to have a starting cost of $20. Right, so we'll put a little squiggly here to show that we are actually not starting our y-axis at 0. We got a little jump there up at 20. And then we will make $2 jumps every time we go above 2 pounds by 1 pound, so another 1 pound increment. So I'm going to go up to 22 pounds on the next step. When I get to 3 pounds, I'll go up to, sorry, I think I said 22 pounds. I meant to say $22. I'm going to go up to $22 as soon as we get above 2 pounds and all the way up to 3. Then 24, then 25, or 26 rather, jump of $2, and 28. So those are the increments of price increases, and then we will start to graph the cost here. So starting at 0 pounds, anything just even slightly above 0 pounds, and going all the way up to 2 pounds. But again, we're not including 0. So what we want is an open circle right there on the 20 at the x equals 0 pounds. And we're going to go all the way up to 2 pounds. And for that whole time, all the way up to a package that weighs exactly 2 pounds, we'll be paying a flat fee of $20. Once we have a package that weighs anything more than 2 pounds, though, we are going to be starting over again, open circle, because remember, if it was exactly 2 pounds, it still was costing us $20. But as soon as we go past 2 pounds, we're going to be paying that $22 all the way up until we hit 3 pounds. And then we'll have to make a jump again. So if I had spaced out my lines better, these should look the first step should be twice as long as the next step, but then all the steps after that are supposed to look the same size. But I just had my spacing a little funky. But then the next step up would be to $26. And then, have I missed any? So $2, 2 pounds, 3 pounds, 4 pounds, 5 pounds, and then all the way up to 6 pounds. So let me make this a little smaller. Here's my 5, I'm going to be right here. And then above that, up to 6 pounds there. All right, so that's pretty much what it's supposed to look like. This step should be a little bit shorter, but again, my spacing is a little funky. So I'm resisting the urge to be a perfectionist and fix it. I'm just going to leave it like it is. So that's how you graph that function. So that's basically how these things work. And so now we can focus on the properties of a greatest integer function, which, remember, when it's written like this, it pairs every real number x with the greatest integer that's less than or equal to itself. So looking at the graph, we could see that the domain for this one is pretty much any value of x. There's no restriction on the domain of x, but there is a restriction on the y values, because the y values are jumps, they're not continuous. So even though the domain is kind of what we're used to seeing with a function, our range is actually going to be a list of values rather than an interval. So the y values are going to be anywhere from negative infinity. So this thing in theory could keep going lower and lower, or higher and higher steps, the stairway to heaven. But we'll just use these ellipsis dots to show that the pattern is going to be the same as we establish it from, say, here. Okay, so we're saying the y values can be -3, -2, -1, 0, +1, +2, +3, and so on in that fashion on each side. F of x is constant, so the function, the y values, are constant on open intervals. So, well, every step is a constant piece. So it's constant on the open interval right here for this one. That would be, it's constantly -3, but just in between x values of -3 to -2. Okay, so we will put that down though as like that, without this. And the reason that we don't include, even though there's a closed dot here, the reason that we don't use a square bracket to include x equals -3 is because something being constant implies motion. As x is changing, y is staying the same. So we're not talking about when x is standing still, which would be if you included x equals -3. We're actually saying as you move between -3 and -2 for x values, we will have a constant y value. Y will stay the same. And then it'll happen again from -2 to -1. And then again from -1 to 0, and so on. It is discontinuous at all integer values in its domain. So what that means is that every time you get to, let's say, where should we start here? I guess let's start at the farthest one over. Right here at x equals -2, there is a hole where you have to make a jump up. So you have to actually pick up your pen to move to here. And that is called a discontinuity. So even though there is still a value available on the function to pair up with x equals -2, we had to make a jump to get to it. So then it is discontinuous at -2. It's discontinuous here where it jumps at -1. There's a jump at x equals 0. There's a jump at x equals 1, and so on. And you can keep going to the left and right, up and down, towards infinities. So that is why it's easier to talk about all integer values in its domain. So that would be all integer values in its domain from -infinity to infinity, which is like this part right here is not enough of an answer on its own. You have to have this entire statement here because it's not discontinuous at every single value in its domain, but at integer values in its domain. So it's important to realize that this is connected here.